Before you close your eyes tonight, I need you to hear this. 6 weeks ago, in March 2026, a team of planetary scientists published a paper that quietly changed everything we thought we knew about the most promising places for life in our solar system. Not on Mars, not on Europa's surface, beneath it, beneath the ice, in oceans that have been sitting under kilometers of frozen crust for billions of years, oceans that, according to this new research, are not cold and still and silent the way we imagined them. They are boiling. Not metaphorically, not in the poetic sense that scientists sometimes use when they want to make a press release sound exciting, boiling, turbulent. They're violently churned from below by heat that has no business existing this far from the sun. Heat generated not by a star, but by something older and stranger. The gravitational pull of Jupiter itself, squeezing and stretching these moons like a hand wringing out a wet cloth, over and over, billions of times, for billions of years. The moons of Jupiter are, from the outside, some of the most inhospitable-looking places in the solar system. Europa is a cracked billiard ball of ice. Ganymede is grey and scarred. Callisto is ancient and cratered beyond recognition. Io is a screaming volcanic nightmare of sulfur and fire. They do not look like places where anything could survive, but beneath the ice of at least 3 of them, something extraordinary has been happening in the dark, and the March 2026 paper, published in the journal Nature Geoscience by a team led by researchers at the Southwest Research Institute in Boulder, Colorado, suggests that what has been happening down there is far more violent, far more active, and, this is the part that matters, far more hospitable to life than anyone had dared to model before. The number that stopped scientists in their tracks was this. In some regions of Europa's subsurface ocean, water temperatures near the seafloor may reach above 100 degrees Celsius, the boiling point of water at sea level on Earth. Except that under the crushing pressure of 100 kilometers of ice and ocean, water does not boil at 100 degrees. It stays liquid, it stays hot, and it circulates, rapidly, violently, and in great churning columns of hydrothermal convection that reach from the rocky seafloor all the way up toward the base of the ice shell. Take a moment with that. An ocean, beneath the ice, boiling at the bottom, and we have been floating past it for decades without knowing. Tonight we are going in. Welcome to Science for Sleep, the place where the universe slows down. If you are here for the first time, I am glad you found this. Stay as long as you like. Make yourself comfortable. There is no rush here. These stories have been waiting billions of years to be told. A few more hours will not hurt them. And if Science for Sleep has become part of your nights, if these journeys have kept you company in the quiet hours, a like on this video and a subscription costs you nothing and means everything. It tells the universe that slow, careful science-rooted storytelling still has a place here. The subscribe button is just below this video. It will take you 2 seconds, and then we can go. Tonight's journey begins 4.5 billion years ago. At the moment our solar system was still a cloud of gas and dust, and the seeds of the strangest oceans in the known universe were already being planted. Let us go. There is a particular kind of silence that belongs to the outer solar system. Out past Mars, past the asteroid belt, past the point where the sun has dimmed to something that looks more like a very bright star than the burning disk we know from Earth. Out there, the silence is not just the absence of sound, it is the absence of warmth. The average temperature in the space around Jupiter sits at around minus 145 degrees Celsius. And at that temperature, the chemistry of life as we understand it stops. Water freezes solid. Gases condense into ices. Everything slows to a near halt. And yet in 1610, a man named Galileo Galilei pointed a telescope he had improved himself, a device only a year old at the time, toward the brightest object in the winter sky, and saw something that no human being had ever seen before. 4 points of light arranged in a line beside Jupiter. Points of light that moved, not like background stars, which stay fixed relative to each other as Earth orbits the pole. These points moved relative to Jupiter. They circled it. In 4 days, Galileo had confirmed what he suspected. These were not stars. They were worlds, orbiting another world. He named them after the lovers of the Roman god Jupiter: Io, Europa, Ganymede, Callisto. The Galilean moons. For 3.5 centuries after Galileo, they were points of light. Beautiful, mathematically precise points of light whose orbital mechanics could be calculated to extraordinary precision, but whose surfaces and interiors remained entirely unknown. They were too far away, too small, too cold-looking to seem like anything other than frozen, dead rocks circling a gas giant. Then, in March of 1979, a spacecraft called Voyager 1 made its closest approach to the Jupiter system, and everything changed. Voyager 1 was not designed to linger. It was on its way to Saturn, and Jupiter was a gravity assist, a way of stealing a little momentum from the largest planet in the solar system to fling itself further out into space. But in the hours around closest approach, its cameras were rolling. And what they returned to Earth was, in the words of mission scientist Bradford Smith, something none of them were prepared for. The first shock was Io. Voyager's navigation team, led by Linda Morabito, noticed a crescent-shaped cloud extending above one of Io's limbs in a navigation image. She thought at first it might be a moon she'd missed. She checked the power log. No moon. She looked again. The cloud was volcanic. Io, the innermost of the Galilean moons, the moon closest to Jupiter's crushing gravitational field, was the most volcanically active body in the solar system. Not in the distant past. Right now. As Voyager flew past, Io was erupting. The second shock came from Europa. Europa's surface, as Voyager's cameras resolved it, was ice. Smooth, relatively crater-free ice, though crisscrossed by a network of dark lines that looked like, and there is no more precise analogy, the surface of a cracked egg. Long, gently curving ridges and valleys, some of them thousands of kilometers long, very few craters, which meant, in planetary science terms, that the surface was young. Something was resurfacing Europa continuously, wiping away the craters that constant bombardment from space should have left. Something beneath the surface was active. The word that appeared in internal memos among Voyager scientists, according to mission records later released by NASA, was the same word that would dominate Europa's science for the next 5 decades. Ocean. But no one could prove it yet, and proof in planetary science takes time. It takes missions. And it takes decades of patience and argument and competing models and falsified hypotheses. It takes instruments that do not exist yet, attached to spacecraft that have not been built yet, travelling to places no human has ever been, to answer questions that were first asked by a man with a handmade telescope in a garden in Padua in the winter of 1610. The proof would come, but first scientists needed to understand what could possibly keep water liquid this far from the sun. And the answer, when it came, was one of the most elegant and unexpected pieces of physics in the entire history of planetary science. The answer was gravity, not the gravity of the sun, the gravity of Jupiter. Io gave scientists the first hint, because Io's volcanic activity needed an explanation. The moon orbits Earth, and Earth's tidal forces stretch and compress the moon slightly with each orbit, but not enough to generate significant heat. Io orbits Jupiter. Jupiter is 1,300 Earths by volume. Its tidal forces on Io are not slight. They are enormous, and Io does not orbit Jupiter in a perfect circle. Its orbit is kept slightly elliptical by the gravitational resonance it shares with Europa and Ganymede, a precise 3:1:2 relationship in which every time Ganymede completes one orbit, Europa completes exactly 2, and Io completes exactly 4. This resonance, discovered mathematically by Pierre-Simon Laplace in 1805 and now called the Laplace resonance, prevents the orbits from circularizing, and which means Io is always being stretched and compressed by Jupiter's changing gravitational pull as it moves closer and farther away in its elliptical path. The stretching and compressing generates heat, in Io's case enough heat to melt its interior entirely, and drive the most violent volcanism in the solar system, with plumes erupting to heights of 500 kilometers and lava lakes the size of small countries. In 1979, just days before Voyager 1's closest approach to Jupiter, 3 scientists, Stanton Peele, Patrick Cassin, and Ray Reynolds, published a paper in the journal Science predicting exactly this. They predicted, based purely on orbital mechanics and tidal heating calculations, that Io should be volcanically active. Their paper was published on the 2nd of March 1979. Voyager 1 returned images of active geovolcanism on the 5th of March 1979, 3 days later. It is one of the most remarkable predictive successes in the history of planetary science, and it immediately raised a question that has driven Europa research ever since. If tidal heating can melt Io's interior entirely, if it can generate enough heat to drive constant global volcanism on a body slightly larger than our moon, what is it doing to Europa? Europa is further from Jupiter than Io. The tidal forces it experiences are weaker. Not weak enough to drive surface volcanism, Europa's surface is ice, not lava. But potentially, and this was the argument that began to be made seriously in the 1980s, potentially strong enough to maintain a layer of liquid water beneath that ice. An ocean, not frozen, liquid. Kept warm not by the sun, but by the rhythmic squeeze and release of Jupiter's gravity. In 1987, a paper published in the journal Icarus by David Reynolds, Stephen Squires, Stanton Peele, and Christopher McKay laid out the case explicitly. They calculated that Europa's subsurface ocean, if it existed, could be up to 100 kilometers deep. They noted that the bottom of that ocean would be in contact with a rocky sea floor. They noted that tidal heating would drive geological activity on that seafloor, and they noted that the combination of liquid water, rock, heat, and chemical gradients, the exact same combination that drives hydrothermal vent ecosystems in Earth's deep ocean, represented in their careful scientific language a potentially habitable environment. In 1987, orbiting Jupiter. The sentence sat in the scientific literature for 38 years, gathering weight, and then, in March 2026, researchers at the Southwest Research Institute finally had the computational tools, the mission data, and the thermal models to answer the question that Reynolds and his colleagues had only been able to gesture toward. How habitable exactly? The answer came in the form of a number: 120 degrees Celsius. That is the temperature that the new models, incorporating data from the Juno spacecraft's gravity measurements, the Hubble Space Telescope's auroral observations, and the Europa Clipper's first gravity mapping passes, calculate may exist at the sea floor of Europa in the most tectonically active regions. 120 degrees Celsius. 20 degrees above the boiling point of water at surface pressure on Earth, deep enough under ice and ocean that the pressure keeps the water liquid. Hot enough to drive powerful hydrothermal convection, hot enough to drive chemistry, hot enough potentially for life. But that number, 120 degrees, is not the most striking thing in the March 2026 paper. The most striking thing is what the models show happening between that hot seafloor and the cold base of the ice shell above. The water moves, not gently, not in slow, lazy currents, in great, rapid, turbulent convective columns, rising columns of hot water that carry heat, dissolved minerals and chemical compounds from the seafloor upward through the ocean, and sinking columns of cold, dense water that descend from the ice base back down toward the rock. And a full vertical circulation that, the models suggest, can complete a cycle from seafloor to ice base in as little as a few decades. On Earth, our oceans take roughly 1,000 years to fully circulate. Europa's hidden ocean, if these models are correct, circulates in decades. The implications of that number are difficult to fully absorb. Life on Earth did not originate in the surface ocean. The best current evidence suggests it originated in deep-sea hydrothermal systems, in alkaline vents or black smoker chimneys on the seafloor, where hot, chemically rich water meets cold ocean water and drives the kind of electrochemical gradients that can power the first metabolic reactions. Life started at the bottom. Then it spread upward and eventually outward, and eventually it covered the planet. In Europa's ocean, the bottom is hot. The chemistry is active, and the entire ocean column is in rapid circulation, meaning that whatever chemistry starts at the bottom gets distributed throughout the entire water column within decades. Not millions of years, decades. This is what the March 2026 paper calls, in its careful scientific language, a highly favourable regime for the emergence and persistence of chemosynthetic life. Let that sit for a moment. We are not talking about ancient Europa. We are not talking about a window of habitability that opened and closed 1 billion years ago. We are talking about right now, tonight. As you listen to this, Europa's ocean is circulating, its seafloor is hot, its chemistry is active, and it has been this way, continuously, for at least 1 billion years. Whatever was going to start down there has had 1 billion years to do it. We do not know if it did. We want to be precise about that. The March 20-26 paper is a modelling study. It predicts conditions. It does not detect life. The question of whether anything actually lives in Europa's ocean remains, as of the moment this script was written, entirely open. But the conditions, according to our best current understanding, are there. They have been there for 1 billion years, and we are, right now, sending a spacecraft to find out. The Europa Clipper launched on the 14th of October, 2024. It is the largest planetary science spacecraft NASA has ever built, a spacecraft with a 30-meter wingspan, 9 scientific instruments, and a mission designed to conduct 49 close flybys of Europa over 3.5 years, beginning in 2030. It is, by any measure, one of the most ambitious planetary science missions ever attempted, and it is already on its way. But Europa is not the only moon in the Jupiter system hiding a boiling ocean. And the story of how we came to understand that, the story of Ganymede and Callisto, the story of the instruments that finally let us see through kilometers of ice, the story of what we found when we looked, that story is stranger and more surprising than almost anyone predicted, because it turns out that the heat is not where we expected it to be. And the ocean that may be closest to the kind of chemistry that produces life is not the one we have been most focused on. The answer, when it comes, is going to require us to completely reconsider which of Jupiter's moons we should be looking at most carefully. And it starts with a measurement that almost nobody noticed, made by a spacecraft that had already been operating for 12 years. Ganymede is the largest moon in the solar system. Larger than Mercury, larger than Pluto, larger in terms of diameter than anything else that orbits another planet in our solar system. If Ganymede orbited the Sun directly instead of Jupiter, it would be classified as a planet without any debate. Its diameter is 5,268 kilometers. Its surface is ancient and scarred, a patchwork of very old, heavily cratered dark terrain and slightly younger, grooved lighter terrain that hints at a period of geological activity long past. From the outside, Ganymede looks dead, cold, grey, ancient and still, and in 1996, the Galileo spacecraft made the first of 6 close flybys of Ganymede and detected something that genuinely surprised the mission team. Ganymede had a magnetic field, not a weak-induced field like Europa's, a genuine intrinsic magnetic field, generated by an active dynamo in its metallic iron core. This made Ganymede the only moon in the solar system known to generate its own magnetic field, a distinction it still holds today, and a magnetic field means a liquid conducting layer somewhere inside the moon, most likely a molten iron core, but the magnetic field, while remarkable, was not what made planetary scientists begin to suspect a subsurface ocean on Ganymede. What made them suspect an ocean was the aurora. Ganymede sits inside Jupiter's enormous magnetosphere, the bubble of magnetic influence that surrounds Jupiter and extends far out into space. Where Ganymede's own magnetic field meets Jupiter's magnetosphere, something happens that is unique in the solar system. A miniature magnetospheric system forms around Ganymede, with its own auroral bands near the poles. These auroras glow in ultraviolet light and can be observed from Earth with the Hubble Space Telescope. In 2015, a team led by Joachim Sauer at the University of Cologne published a paper in the Journal of Geophysical Research describing what they found when they watched Ganymede's auroras rock back and forth. The auroras did not rock as much as they should have. The rocking motion of an aurora responds to changes in the surrounding magnetic field, and the degree of rocking tells you something about what is inside the moon. If Ganymede had no subsurface ocean, the auroras should rock by about 6 degrees. They rocked by only about 2 degrees. The suppressed rocking meant that something inside Ganymede was dampening the magnetic response, something electrically conducting, something that would generate its own induced magnetic field in opposition to Jupiter's changing pull, something like a saltwater ocean. The paper calculated the depth of the ocean at between 800 and 900 kilometers below Ganymede's surface, buried under a thick shell of high-pressure ice, but there, and potentially global in extent. The volume of water in Ganymede's subsurface ocean, if the models are correct, is approximately 25 to 35 times the volume of all of Earth's oceans combined. 25 to 35 times. In a moon that from the outside looks like a grey dead rock. But the March 20-26 paper's contribution to our understanding of Ganymede is not the existence of the ocean. That has been suspected since 2015 and confirmed to high confidence by the Hubble measurements and subsequent Juno gravity data. The contribution is the heat. Previous models of Ganymede's interior had suggested that tidal heating in Ganymede would be minimal. Ganymede is the outermost of the Laplace resonance moons, and the resonance keeps its orbit slightly elliptical, but not as elliptical as Io's or Europa's. The assumption was that Ganymede's ocean, while vast, would be relatively cold and chemically inert, a giant body of water kept liquid by the pressure of the ice above it and a slow, modest flux of heat from radiogenic decay of rocky elements below. The March 2026 paper challenges that assumption directly. Using refined gravity data from Juno's extended mission and new models of Ganymede's orbital evolution over the past billion years, the team found that Ganymede almost certainly experienced periods of significantly higher tidal heating in its past, periods when its orbital resonance was stronger, its tidal deformation was more pronounced, and the heat flux into its ocean from below was substantially higher than present estimates suggest. The seafloor temperatures during these periods, the models calculate, may have reached between 80 and 110 degrees Celsius. And the team's most striking finding is this. The thermal signature of those ancient high heat periods may still be present in Ganymede's ocean today. Not as active heating, the resonance has relaxed somewhat, but as residual chemical enrichment. Hot hydrothermal activity dissolves minerals from rock. It creates chemical gradients. It builds complex molecular structures, and once those structures exist in a large, stable, slowly circulating ocean, they persist. They do not simply disappear when the heat source weakens. They circulate. They react with each other. They potentially accumulate into greater complexity over millions, then hundreds of millions, then billions of years. What the March 20-26 models suggest, in their careful, hedged, peer-reviewed language, is that Ganymede's ocean may contain the chemical legacy of a billion years of intermittent hydrothermal activity, a library of complexity written in dissolved minerals and organic compounds and electrochemical gradients, accumulated slowly in a vast dark ocean under a kilometre of ice, with no sunlight, no seasons, no surface to speak of, and no reason that anything we know of could not, in principle, be alive in it. We do not know if anything is, but the library is there. And the strangest part of the March 20-26 paper is not Europa. It is not Ganymede. It is the moon that almost nobody expected. It is Callisto. Callisto is, in the conventional view of planetary science, a world that missed its moment. It is the outermost of the 4 Galilean moons, and orbiting Jupiter at a distance of nearly 2 million kilometres, far enough from Jupiter that the Laplace resonance does not include it. Callisto's orbit is nearly perfectly circular. It experiences almost no tidal forcing. Its surface is the most heavily cratered of any large body in the solar system, a testament to billions of years of impact bombardment and absolutely no geological activity to erase the record. Every crater that has ever hit Callisto is still there, perfectly preserved, going back to the earliest era of solar system bombardment 4 billion years ago. Callisto has been described in various planetary science papers as geologically dead, as a world frozen in time, as a body that formed and then simply stopped. And yet, in 2001, the Galileo spacecraft's magnetic field measurements at Callisto showed the same kind of induced magnetic field signature that was interpreted as evidence of a subsurface ocean at Europa and Ganymede. The signature was weaker, but it was there. Planetary scientists were puzzled. Where was the heat coming from to keep water liquid inside Callisto, with no tidal forcing and a surface suggesting complete geological inactivity? The answer, over the following 2 decades, turned out to be radiogenic heating, the slow, steady decay of radioactive elements in Callisto's rocky interior, generating heat that has been trickling upward through the moon's interior since its formation. Not dramatic, not violent, but continuous. And over 4 billion years, even a trickle accumulates. The March 2026 paper adds a new dimension to Callisto's ocean story. Using models that incorporate updated estimates of Callisto's bulk composition from recent observations, the team finds that Callisto's ocean, while almost certainly colder than Europa's or Ganymede's, may be in a chemical state that is, in some respects, more interesting than either. Because Callisto's ocean has had 4 billion years, the full age of the solar system, to slowly interact with its rocky interior. 4 billion years of slow, low-temperature aqueous chemistry, 4 billion years of mineral dissolution, 4 billion years of chemical accumulation. The team uses a word that appears only once in the paper, in the discussion section, in a sentence that is easy to miss if you are reading quickly. The word is prebiotic chemistry. The chemistry that precedes life. The reactions that build amino acids, nucleotides, lipids, the molecular building blocks from which life on Earth assembled itself. Prebiotic chemistry requires liquid water, chemical feedstocks, an energy source, and time. Callisto's ocean has all four, and it has had more time than any other ocean in our solar system. This is not a claim that Callisto has life. It is a claim that Callisto's ocean may be, chemically, the most prepared for life of any body we have studied. The most prepared, after the most time, in a moon that from the outside looks completely dead. The universe has a particular fondness for hiding its most interesting things in its most unlikely-looking places. It is worth pausing here, in the middle of this journey, to consider what it means to have an ocean you cannot see. That Europa's ocean is separated from space by a shell of ice that is, depending on which region you are looking at and which model you believe, between 15 and 30 kilometers thick. To put that in perspective, the deepest borehole ever drilled on Earth, the Kola super deep borehole in Russia, which took 24 years to drill and represented the most ambitious deep drilling project in human history, reached a depth of 12.2 kilometers before the rock became too hot and too plastic to drill further. We have never penetrated 15 kilometers of anything. Europa's ice is not just thick, it is dynamic, it moves. The March 2026 paper includes a section on ice shell dynamics that adds another layer of complexity to what is already a staggeringly complex system. Europa's ice shell is not a simple uniform slab, and it is differentiated, warmer, softer, more mobile at its base, where it meets the liquid ocean, and colder, harder, more rigid at its surface, where it faces space at temperatures of minus 170 degrees Celsius. The boundary between these two regimes is called the brittle ductile transition, and it migrates up and down depending on the local heat flux. In regions of high tidal heating, the base of the ice shell may be close enough to the surface that warm, ocean-influenced ice can reach within a few kilometers of the surface. This is why Europa's surface looks the way it does, cracked, ridged, disrupted. The ice above a warm, active ocean does not stay still. It flexes, it fractures. It sometimes, the models suggest, allows ocean water to directly contact the surface, and either through cryovolcanic eruptions or through the slow upwelling of briny, chemically enriched slush through fracture systems. The Hubble Space Telescope observed what appeared to be water vapor plumes above Europa's surface in 2012 and again in 2016. The observations were controversial. The plumes were at the very edge of Hubble's detection capability, and subsequent attempts to confirm them produced ambiguous results. But if the plumes are real, if Europa is actively venting material from its subsurface into space, then there is something extraordinary waiting for us. Material from Europa's ocean, chemistry from Europa's seafloor, floating free in space, available to be sampled without landing, without drilling, without penetrating 30 kilometers of ice. All we would need to do is fly through it. The Europa Clipper is designed to do exactly that. Among its 9 instruments is a mass spectrometer capable of analysing the composition of particles and gases in Europa's thin exosphere, the almost vacuum that surrounds the Moon. If the plumes are real, Clipper will fly through them on its closest approaches and taste whatever Europa is putting into space. The Europa Clipper team has been careful not to overpromise. The mass spectrometer can detect organic compounds, but detecting organics is not the same as detecting life. Finding amino acids or lipids in Europa's plumes, if there are plumes, would be extraordinary. It would be the most significant astrobiological finding in human history. But it would not prove life. Life is a process, not a molecule. And a dead ocean with its active hydrothermal chemistry can produce all the same organic molecules that life produces, without any of the biology. Proving life, if it is there, will require something more. It will require, eventually, getting down through the ice and into the ocean. Looking directly, and that is a mission for the future, a mission that, as of 2026, exists only as a concept study called Europa Lander, which NASA's Planetary Science Decadal Survey has recommended for development, but which has not yet received formal approval or funding for flight. It may be the most important mission humanity ever attempts. It may also be the hardest. Consider what drilling 15 to 30 kilometers through ice on a moon 400 million miles from Earth with no human operators present in real time actually requires. The communication delay between Earth and Jupiter varies between 33 and 53 minutes each way, depending on where both planets are in their orbits. A command sent from Earth takes up to 53 minutes to arrive. A response takes another 53 minutes to return. You cannot have a real-time conversation with a drill on Europa. Everything it does, it must decide for itself. The entire mission must be autonomous in ways that our current technology is only beginning to approach. The ice itself presents challenges that no Earth-based engineering experience has fully prepared us for. Terrestrial ice drilling, even in Antarctica, deals with ice that is relatively warm, relatively soft, and relatively homogeneous. Europa's ice is cold to a degree that changes its mechanical properties fundamentally, and it is likely to contain salts and other inclusions that alter its thermal conductivity and drilling behavior unpredictably. And as you drill down, you enter the region where the ice becomes warmer and softer and the ductile regime, and the borehole begins to close behind the drill. You cannot simply drill down and pull the drill back up. You need a system that can keep the hole open, or that does not need the hole to stay open, or that can operate in conditions where the ice is actively trying to swallow it. These are engineering problems that some of the best minds at NASA, ESA, and a dozen universities are currently working on. They are not unsolvable. They are merely very, very hard. And there is a particular kind of beauty in the fact that the hardest engineering challenge humanity has ever attempted is being driven by a question so simple a child could ask it. Is there anything alive down there? We have been asking that question about Europa specifically since the Voyager flybys of 1979. We have been asking it more seriously, with better tools and better models, since the Galileo mission of the 1990s. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, flew within 350 kilometers of Europa's surface on its closest approach, close enough to detect the induced magnetic field, close enough to image the surface in extraordinary detail, close enough to measure the composition of the thin exosphere, close enough to make the ocean feel real. Galileo's mission ended on the 21st of September 2003, when mission controllers deliberately commanded the spacecraft to plunge into Jupiter's atmosphere and burn up. The reason was contamination prevention. The spacecraft's fuel was running low, and without controlled propulsion, it might eventually impact Europa, potentially contaminating the moon's surface with the Earth microbes that had hitchhiked on the spacecraft despite sterilization protocols. The decision was made to sacrifice the spacecraft rather than risk compromising the very place it had done so much to make us want to visit. There is something almost literary about that ending. A spacecraft that spent 8 years orbiting Jupiter, transforming our understanding of Europa and the other Galilean moons, going to its death in the clouds of Jupiter rather than risk tainting the ocean it had revealed. The silence after Galileo was long. It was filled in the years that followed with papers and models and debates and budget cycles and competing mission concepts. Europa had advocates, passionate, vocal, scientifically credentialed advocates, who argued at every opportunity that Europa represented the single most compelling astrobiological target in the solar system and deserved a dedicated mission. They argued this for more than 20 years, through multiple administration changes and budget crises and shifting space agency priorities. They won. The Europa Clipper is their victory. And it is, in a sense, the victory of the question itself, of the simple, urgent, the four-word question that Galileo's data planted so deeply in the scientific community that it could not be ignored, no matter how expensive or technically difficult the answer would be to pursue. Is there anything alive? The Clipper launched in October 2024. It will arrive at the Jupiter system in April 2030 after a 5.5-year journey. Its first Europa flyby is scheduled for June 2031, and over the following 3.5 years, it will map Europa's surface, measure its magnetic field in unprecedented detail, characterize its ice shell thickness, search for active plumes, and taste whatever is in the exosphere on its 49 close passes. 49 passes, each one a data point, each one a closer look at the thing we most want to understand. But there is something worth saying here about the timescale of planetary science that is easy to miss when you're reading a paper or watching a news story about the latest discovery. The people who first seriously proposed a Europa mission in the late 1980s, people like John Delaney and Ron Greeley and David Morrison, who argued in NASA internal documents and at scientific conferences that Europa deserved its own spacecraft. Most of them did not live to see the Clipper launch. The mission that their advocacy made possible launched 40 years after they began advocating for it. 40 years. In one human lifetime, the question went from a paper in Icarus to a spacecraft on its way to answer it. That is, by the standards of big science, extraordinarily fast, by the standards of human life. And it is long enough that the people who asked the question first never heard the answer. There is something quietly melancholy about that, and something quietly inspiring. The questions we ask today, the missions we advocate for, the data we argue should be collected, some of them will not be answered in our lifetimes. Some of them will be answered by people who have not been born yet, using instruments that have not been designed yet to explore places no human has ever been. And those people, when they find what they find, will stand on the shoulders of the arguments that were made and the data that was collected and the missions that were funded because of what the people before them believed was important. This is how science works. It is not a single moment of discovery. It is a relay. And a passing of questions from one generation to the next, each generation carrying them a little further. The March 2026 paper is one more step in that relay. But we have not yet talked about the finding in the paper that may, in the long run, matter most. We have talked about temperature. We have talked about circulation. We have talked about prebiotic chemistry. What we have not yet talked about is the interface. The ice-ocean interface. Where the base of the ice shell meets the top of the liquid ocean is, according to the March 2026 models, one of the most chemically active regions in any of Jupiter's moons, and the reason has to do with radiolysis. Jupiter's radiation environment is severe. Europa sits deep inside Jupiter's radiation belts, zones of high-energy charged particles trapped by Jupiter's magnetic field and accelerated to near-relativistic speeds. The radiation dosage on Europa's surface is roughly 540 rem per day. A dose of 500 rem over a short period is lethal to most Earth organisms. Europa's surface is, in radiation terms, one of the most hostile environments in the solar system. But radiation is not only destructive. At the surface of Europa's ice, the constant bombardment of high-energy particles from Jupiter's radiation belts drives chemical reactions that would not otherwise occur. Water ice is split into hydrogen and oxygen. Sulfur-bearing compounds from Io's volcanic plumes, which have coated part of Europa's surface, are processed into sulfates and sulfuric acid. And carbon dioxide, molecular oxygen and hydrogen peroxide are produced continuously at the surface. These oxidants accumulate, and then, this is the key, they are paid. Europa's ice is not static. The surface is continuously turned over by geological processes, and material from the surface is, over geological time, mixed downward through the ice shell. The March 2026 paper includes an updated calculation of the oxidant delivery rate to Europa's ocean, the rate at which surface-produced oxidants make their way down through the ice and into the liquid water below. The updated number is higher than previous estimates, significantly higher. And oxidants are, from the perspective of astrobiology, critically important. Life on Earth, at its most fundamental level, that is a redox reaction, a transfer of electrons from one molecule to another, releasing energy that can be used to do biological work. In Earth's ocean, the redox chemistry that drives aerobic life depends on oxygen as the terminal electron acceptor. Oxygen comes from photosynthesis. Photosynthesis requires sunlight. Europa's ocean has no sunlight. No photosynthesis, no oxygen produced biologically. But if oxidants from the surface are being delivered to the ocean at the rate the March 2026 models suggest, then Europa's ocean may have a supply of oxidants. Not oxygen exactly, but chemically equivalent electron acceptors like hydrogen peroxide and sulfate that could, in principle, support a chemosynthetic biosphere without any sunlight at all. Not a biosphere dependent on the sun, a biosphere dependent on Jupiter's radiation belts, which have been bombarding Europa's surface and driving oxidant production continuously for at least 1 billion years. Jupiter in this model is not just the gravitational engine that keeps the ocean liquid. It is also, inadvertently, the power source that makes the ocean's chemistry interesting enough to support life. The gas giant that looks from a distance like nothing but a beautiful swirling storm system turns out to be the silent architect of potentially habitable worlds orbiting around it. If you are still with me, if this journey has kept you company tonight, I want you to know that your being here matters. A like on this video, and a subscription to Science for Sleep. These small gestures are what allow us to keep making these journeys. The subscribe button is just below, and now let us continue, because we are not done. But we have talked about what these oceans might contain, we have not yet talked about what it would mean if they do. There is a concept in astrobiology called the second genesis. The first genesis, the origin of life on Earth, happened once, approximately 3.8 billion years ago, in a set of circumstances that we do not fully understand, using chemistry that we are only beginning to reconstruct in an environment that no longer exists in quite the same form. We have one example of life beginning, one data point. And from one data point you cannot tell whether life is common or rare. You cannot tell whether it was almost inevitable, given the right conditions, or whether it was a staggering improbability that has only ever happened once in the entire history of the universe. One data point is not science. It is a story. The second genesis would change that. A second origin of life, independent of Earth's, using potentially different chemistry and potentially different conditions, would tell us something no single data point can. It would tell us that life, given the right environment and enough time, is not a miracle. It is a consequence. That is why Europa matters so much. Not because any individual organism in its ocean would be intrinsically important. A microbe in a dark ocean under the ice of a moon is, in itself, a fairly unremarkable thing. What would be remarkable is what it would mean. A second genesis, in our own solar system, in a body we have known about for 400 years, in a place we could reach with a spacecraft and an instrument package, would be the most significant discovery in the history of science. And not just the history of space exploration, the history of science. It would mean that life, wherever the conditions are right, happens. And the conditions, liquid water, chemical energy, time, are not rare. They are scattered across the universe in oceans we are only beginning to find. The March 2026 paper does not use the phrase second genesis. Scientists are careful with language. They use words like potentially habitable and chemical precursors and conditions consistent with life's requirements. These are the right words, the honest words, the words that do not overclaim. But underneath the careful language, the implication is clear. The conditions are there. They have been there for 1 billion years, and we are, for the first time in history, close enough to finding out, with instruments in space, on their way. But right now, Omne, that the question is no longer theoretical. Let us talk about what happens next, because the story of Jupiter's icy moons does not end with the Europa Clipper, or with the March 2026 models, or with any single mission or paper. It is a story that is still being written, and the next chapters are already in preparation. ESA's JUICE mission, the Jupiter Icy Moons Explorer, launched in April 2023 and is currently en route to the Jupiter system, scheduled to arrive in July 2031. While the Europa Clipper focuses almost exclusively on Europa, JUICE will conduct close flybys of both Callisto and Europa before entering orbit around Ganymede in 2034, making it the first spacecraft ever to orbit a moon other than our own. JUICE carries 10 scientific instruments and will spend years studying Ganymede's magnetic field, surface. It's an interior in unprecedented detail, Together, JUICE and Europa Clipper represent a coordinated scientific campaign at the Jupiter system. Unlike anything attempted before, two spacecraft from two space agencies approaching from different angles, measuring complementary things, building a picture of these ocean worlds that neither mission could construct alone. The combined data will be transformative. We will know the thickness of Europa's ice shell with far greater precision than we do today. We will know the salt content of Europa's ocean from the magnetic field response. We will know whether Ganymede's ocean is in contact with its rocky seafloor, and or whether it is sandwiched between layers of high-pressure ice that insulate it from both the rock below and the ice above. A configuration that would dramatically reduce its habitability by cutting off the chemical exchange between ocean and rock that drives hydrothermal chemistry. We will know whether Callisto's ocean is real, or whether the magnetic signal Galileo detected was an artifact of something more complicated in its interior. And we will know whether Europa has active plumes. If it does, if the Europa Clipper's mass spectrometer detects complex organic molecules in Europa's exosphere on its closest flybys, that will not be the end of the story. It will be the beginning of the next conversation. The conversation about whether to send a lander, whether to attempt a drill, whether to commit to the mission that answers the question directly. The hardest, most expensive, most technically ambitious mission in human history, driven by the simplest question human beings have ever asked. Are we alone? There is a particular quality to the darkness in the outer solar system that is worth sitting with for a moment. The sun from Jupiter's distance is a bright point of light, not a disk, not the warm, sprawling presence that fills our sky and drives our days and warms our skin. A point, bright enough to cast sharp shadows on the surface of Europa, but not warm enough to be felt, not warm enough to melt anything. The ice of Europa's surface is as cold as the sun can make it at this distance, and that temperature is minus 170 degrees Celsius, and yet 100 kilometers below that surface. And in the dark, under all that ice, the temperature at the seafloor is perhaps 120 degrees above zero. The range from the surface to the seafloor, from the face that looks at the sun to the face that rests on the rock, is nearly 300 degrees. 300 degrees of difference, in a moon smaller than our own. All of that heat comes from inside, from the rock, from Jupiter's gravity, not from the sun. The sun is irrelevant to what happens at Europa's seafloor. The chemistry at the bottom of that ocean happens in complete independence of the star at the center of our solar system. This is why the March 20-26 paper matters beyond the specifics of Europa and Ganymede and Callisto. It matters because it is part of a growing body of evidence that habitable environments, places where liquid water and chemical energy and time exist in the right combination, do not require a star, they do not require sunlight, they do not require the kind of planetary positioning that we call the habitable zone, that narrow band of distance from a star where liquid water can exist on a planet's surface. The habitable zone is a concept designed for surface life. For life like ours, dependent on sunlight, living on a rocky surface in contact with a warm atmosphere. It is a useful concept. It has guided the search for exoplanets for decades. But Jupiter's moons suggest a different kind of habitability. Subsurface habitability. Ocean world habitability. Habitability that depends not on where a body sits relative to its star, but on how it sits relative to its planet. On whether the tidal forces acting on it are strong enough, steady enough, and long-lasting enough to keep an ocean liquid in the dark, and tidal forces depend on orbital mechanics, on mass ratios and resonances and eccentricities that are independent of where the whole system sits relative to a star. A giant planet in a very cold system, far from any star, a rogue planet, a free-floating world, a body that has no star at all, could in principle maintain tidal forces strong enough to keep the oceans of its moons liquid, could, in principle, host the same kind of subsurface ocean worlds that orbit Jupiter, in the dark, between the stars, far from any light. The universe is larger than the habitable zone, far larger. We are right now at a moment in the history of science that future generations will look back on, the way we look back on the moment Galileo pointed his telescope at Jupiter and saw 4 points of light that moved. We are at the moment before, the moment when the question is fully formed and the answer is within reach, but not yet in our hands. The moment when we know enough to know what we do not know. The moment when the spacecraft is on its way. where are you listening from tonight? Wherever you are, if you can see the sky, Jupiter is visible to the naked eye for much of the year, a steady, bright, cream-coloured point of light that does not twinkle the way stars do. Planets, being disks rather than points, are large enough that atmospheric turbulence does not scatter their light the same way it scatters the light of distant stars. As they shine steadily, they are, once you know what to look for, unmistakable. If you have a pair of binoculars, even cheap ones, even the kind that have been sitting in a cupboard for years, and Jupiter is above your horizon tonight, you can see what Galileo saw. 4 points of light arranged and in a line beside the planet. Sometimes all 4 are visible, sometimes 1 or 2 are hidden behind the planet or in its shadow. But on a clear night, with even modest optical aid, you can see them. What you cannot see, obviously, is what is beneath their surfaces. You cannot see the oceans, you cannot see the heat. You cannot see whatever, if anything, moves through the water in the dark 100 kilometers under the ice, but you can know it is there. And there is something in that. In the act of looking at a point of light and knowing that beneath its frozen surface an ocean is circulating in the dark, carrying heat from a seafloor warmed by a gas giant's gravity, mixing chemistry that has been accumulating for 1 billion years, there is something in that knowing that changes the point of light. It is not a point of light anymore. It is a world with an ocean, and maybe, just maybe, with something in it. The light you are seeing if you go outside and look at Jupiter tonight left its surface about 33 to 53 minutes ago, depending on where Earth and Jupiter are in their orbits. It crossed 400 million miles of cold space to reach your eyes, and in that time, in those 30 to 50 minutes of light travel, the ocean beneath Europa's ice kept circulating. The seafloor kept generating heat. The chemistry kept reacting. It has been doing this without interruption for 1 billion years. It will keep doing it tonight. It will keep doing it while you sleep. And somewhere in a control room, a team of engineers and scientists are watching data from a spacecraft that launched in October 2024 and is right now crossing the outer solar system, carrying instruments designed to ask the oldest question in the most direct way we have ever managed to ask it. The answer is coming. Not tonight, not this year, but within the decade of your life that you are currently living. Sometime between now and approximately 2035, the Europa to Clipper will make its 49 passes. JUICE will settle into Ganymede orbit. The data will come back, the papers will be written, and beneath it the ocean moves. There is something that planetary scientists do not often say in papers, something that lives in the margins of conference presentations and in the conversations that happen after the formal sessions are over, when the recorders are off and the careful language of peer review does not apply, something that the data keeps nudging toward without ever quite arriving. The something is this. We have been assuming in most of our models of subsurface ocean habitability that life, if it exists in these oceans, would be microbial, simple, single-celled, the kind of thing you would need a microscope to see, the kind of thing that would leave chemical traces rather than physical structures, the kind of thing that would be, in the grand drama of biology, a very quiet first act. And that assumption may be correct. The deep-sea hydrothermal ecosystems on Earth, the ones that live without sunlight and drive their metabolism entirely from chemical energy, are dominated by microbes, bacteria and archaea primarily. Chemolithotrophic organisms that extract energy from reactions between hydrogen and carbon dioxide, or between hydrogen sulfide and oxygen, or between iron compounds in different oxidation states. They are extraordinary in their adaptations, they are ancient in their lineages, but they are small. However, Earth's deep-sea hydrothermal ecosystems are not only microbial, and the hydrothermal vents of the mid-ocean ridges, the black smokers and the white smokers, and the more recently discovered alkaline vents like the Lost City Field in the Atlantic, the chemical energy produced by the vents supports entire ecosystems that extend far beyond the microbes. Tube worms 3 meters long, giant clams, shrimp with photoreceptors on their backs sensitive to the faint infrared glow of the vent fluid, crabs, fish, full ecological communities in complete darkness, at crushing pressures, with no sunlight anywhere in the energy chain. These communities are built on a microbial foundation. The chemosynthetic microbes are the primary producers, the organisms at the base of the food web, The ones doing the work of capturing chemical energy and converting it into organic matter. Everything else eats them. Nor eats the things that eat them. But the point is that the ecosystem does not stop at the microbes. Given enough chemical energy, given enough time, given enough evolutionary pressure, simple microbial foundations can support complexity, can support multicellular life, can support things with bodies, with behavior, with ecologies. Europa's ocean has been warm for at least 1 billion years. Earth's first multicellular animals appeared approximately 600 million years ago, in the Ediacaran period, after roughly 3 billion years of microbial life. The interval between the first life and the first multicellular animals was 3 billion years on Earth. Europa's ocean has been habitable, if it has been habitable at all, for somewhere between 1 and 4 billion years depending on the model. The numbers are not a prediction. They are not even a suggestion. But they are worth holding in mind when you picture what might be in that ocean. Because the honest answer, the answer that the data does not rule out, is not necessarily limited to what you could see under a microscope. We do not know. We want to be precise about that. We genuinely do not know. The question of whether Europa's ocean contains life of any kind remains entirely open. But the question of what kind of life, if life is there, is also open. And it is a question that planetary scientists are beginning to discuss more openly as the models of chemical energy availability grow more detailed and the estimates of the ocean's age grow longer. There is a particular silence that surrounds these discussions in the scientific literature, a careful, deliberate silence. And because suggesting that a subsurface ocean might contain complex life, life with bodies, life that swims, life that does anything more interesting than metabolize quietly in the dark, is the kind of suggestion that can make a scientist sound more like a science fiction writer than a planetary scientist. The professional risk of overclaiming in astrobiology is real and has burned careful careers, so the papers stay careful. They talk about chemical energy budgets and oxidant delivery rates and prebiotic chemistry windows. They do not talk about what swims, but the ocean is deep and wide and old and warm at the bottom, and the universe, in our experience, tends to fill available niches. Let us come back to the ice. The ice of Europa's shell is not merely a barrier. It is, according to the March 2026 paper and a substantial body of prior work, an active participant in the chemistry of the system it covers. The ice shell does not simply sit on top of the ocean and insulate it. It exchanges material with it. It processes radiation from above and delivers the products downward. It deforms under tidal forces and creates geological features on the surface that tell us things about the ocean below. The features are remarkable, and they deserve more attention than they usually receive. The most common surface feature on Europa is the ridge, a double ridge, specifically, consisting of 2 parallel raised walls separated by a central trough, sometimes running for hundreds or thousands of kilometers across the surface. When Voyager 2 first imaged Europa in 1979, these ridges were visible but unexplained. The Galileo mission's high-resolution camera resolved them in extraordinary detail and made the mystery deeper rather than shallower. The ridges are too regular to be random. They are too long to be simple fractures. They occur in patterns that suggest systematic repeating geological processes. A 2022 paper in Nature Communications, led by Riley Kullberg at Cornell University, proposed the most compelling explanation yet. Kullberg's team identified a ridge structure on Greenland's ice sheet that was, in miniature, strikingly similar to Europa's double ridges. The Greenland ridge formed when liquid water near the surface of the ice refroze, pushing ice upward on both sides of a central crack and creating a double ridge structure. The mechanism requires subsurface liquid water, not a deep ocean, but a shallow pocket of water close to the surface, what glaciologists call a brine lens. If Europa's ridges form by the same mechanism, it implies that the liquid water, brine chemically enriched from the ocean below, exists in pockets close to Europa's surface, not just at the base of the ice shell, 100 kilometers down, close to the surface, within kilometers of the vacuum of space. The implications are significant on several levels. First, it means that chemical exchange between the ocean and the surface works in both directions, not just surface oxidants working their way down, but ocean chemistry working its way up. Ocean material chemistry from the seafloor, traces of whatever the ocean contains, could be present within a few kilometers of Europa's surface. The second, and this is the part that makes astrobiologists pay attention, it means that the shallow ice of Europa may contain preserved samples of ocean chemistry from different geological periods. Ice is an extraordinary preservative. The deep ice cores drilled from Antarctica preserve atmospheric chemistry, volcanic ash layers, and biological material going back 800,000 years. Europa's ice has been cycling for much longer. A drill that could reach the shallow brine lenses, not the full depth of the ocean, just a few kilometers down to a brine pocket, might find ocean chemistry preserved from millions of years ago. A drill a few kilometers deep is still an extraordinary engineering challenge, but it is a less extraordinary challenge than a drill 100 kilometers deep. And the March 20-26 paper notes, in its final section, that the updated models of shallow brine lens formation suggest these pockets may be more widespread and more accessible than previously thought. There is a potential mission architecture that does not require drilling to the ocean, that does not require penetrating the full depth of the ice shell, that requires only reaching the shallow chemistry that the ocean has already delivered upward to meet us. That is still, by every measure, a mission decades away from flying, but the target has moved closer. The ice is thinner in some places than we thought. Now let us go deeper into what the March 20-26 paper says about the most recent addition to our understanding of these ocean worlds. A section of the paper that received almost no coverage in the science press buried in the supplementary materials, listed as a secondary finding. It is, in my assessment, the most important finding in the paper. It concerns the age of the oceans. One of the fundamental questions about Europa's subsurface ocean, a question with the direct implications for habitability, is how long it has been liquid. A young ocean, one that formed recently in geological terms, has had less time for chemistry to develop, less time for potential life to evolve, less time for complexity to accumulate. An old ocean, one that has been liquid for billions of years, has had the full span of geological time available. Previous estimates of Europa's ocean age have varied considerably. Some models suggested the ocean formed early in solar system history, within the first few 100 million years, that when radiogenic heating from the decay of short-lived radioactive isotopes was intense enough to melt the interior. Other models suggested the ocean is more recent, kept liquid by tidal heating alone, which only became significant after the Laplace resonance was established. When exactly the Laplace resonance was established is itself a question with a range of answers in the literature. The resonance involves all three of the inner Galilean moons, Io, Europa, and Ganymede, and its establishment required a sequence of events involving orbital migration and resonance capture that occurred at some point in the early solar system. The timing is constrained by dynamical models of the early Jupiter system, and those constraints, as of 2024, place the likely establishment of the resonance somewhere between 1 and 4 billion years ago. 1 and 4 billion years is not a narrow range. The difference between an ocean 1 billion years old and an ocean 4 billion years old is 3 billion years of potential chemistry, 3 billion years of potential biological evolution. The range was, for astrobiology, frustratingly wide. The March 20-26 paper narrows it. Using data from Juno's extended mission, specifically detailed gravity measurements of Io that constrain the current rate of tidal dissipation in Io's interior, combined with backward-in-time dynamical modelling of the resonance's evolution, the team calculates a most likely age for the establishment of the current Laplace resonance of approximately 3.2 billion years ago, with an uncertainty of plus or minus 400 million years, 3.2 billion years, Europa's ocean. And under this model has very likely been liquid for at least 2.8 billion years, almost certainly liquid for 3 billion years, possibly liquid for longer, 3 billion years. To put that in context, complex multicellular life on Earth appeared 600 million years ago. Simple multicellular life appeared perhaps 1 billion years ago. The last common ancestor of all life currently living on Earth, the organism from which every bacterium, archaean, plant, fungus and animal descends, lived approximately 3.8 billion years ago. If Europa's ocean has been liquid for 3 billion years, and if life started in that ocean anywhere in the first 800 million years of its liquid history, which is when life started on Earth in rough terms, and after the oceans cooled enough to be habitable, then life in Europa's ocean has had approximately 2 billion years of continuous habitable conditions to evolve in. 2 billion years. On Earth, 2 billion years ago, life had only just invented the eukaryotic cell, the complex nucleus-bearing cell type from which all plants, animals and fungi descend. 2 billion years of evolution from that point produced everything from oak trees to blue whales to the human being reading these words. 2 billion years is not nothing. 2 billion years is, by the standards of biology, an enormous amount of time. We are not saying life is in Europa's ocean, we want to repeat that clearly. We are saying that if it started, if the chemistry crossed the threshold, then if the first self-replicating molecule formed in the right hydrothermal vent at the right moment, then it has had enough time. More than enough time. It has had enough time to become whatever it is going to be. And we are sending a spacecraft to find out. There is one more thing the March 2026 paper addresses that we have not yet discussed, a finding that sits in the intersection of geology and chemistry and feels, when you think about it carefully, almost designed to be noticed. It concerns the composition of the dark material on Europa's surface. Europa is not uniformly white. Its icy surface is crossed by dark reddish-brown material concentrated in the ridges and disruption zones, the very features that are most geologically active, most closely connected to the ocean below. That the dark material is one of the longest-standing mysteries of Europa science. It is not ice, it is not silicate rock. Its spectral signature in infrared light is complex and does not match any simple mineral or salt compound cleanly. Various explanations have been proposed over the decades. Sodium chloride, processed by radiation, magnesium sulfate, sulfuric acid hydrate, hydrogen peroxide, organic compounds. None of these alone fits the spectral data perfectly. The dark material looks like a mixture, a complex radiation-processed mixture of salts and sulfur compounds and possibly organic molecules, derived from the ocean below and altered by Jupiter's radiation belt at the surface. In 2019, a team using the Hubble Space Telescope's infrared spectrograph identified sodium chloride, table salt, as a significant component of the dark material in the geologically young Tara Regio region of Europa's surface. Sodium chloride does not form on ice surfaces naturally. It has to come from somewhere, and the most logical source is the ocean below, a saltwater ocean, delivering sodium chloride to the surface through the geological processes that form ridges and disrupted terrain. The March 2026 paper incorporates the most recent spectral data from the James Webb Space Telescope, which observed Europa in September 2023 and detected carbon dioxide concentrated in the Tara Regio region. Not carbon dioxide from space, carbon dioxide with a spectral signature consistent with having been processed in a liquid water environment. A carbon dioxide that, according to the Webb team's analysis, most likely came from within Europa's ocean. Carbon, from the ocean, on the surface. Carbon is the backbone of organic chemistry, the backbone of life as we know it. Its presence in the surface material of Europa, concentrated in the same geologically active regions where ocean chemistry reaches closest to the surface, is not proof of anything biological. Carbon chemistry is abundant in the solar system. Comets and asteroids deliver it everywhere, but its specific signature in the Webb data, the way it appears to have been processed in a water environment before reaching the surface, adds another data point to a picture that is becoming piece by piece difficult to look at without a particular feeling, the feeling that something interesting is happening in there, that the feeling is not science, but it is the thing that drives science, the feeling that something is worth looking at more carefully, the feeling that the answer, when it comes, will matter. Let us slow down now. We have travelled a long way tonight. We started in a garden in Padua in 1610, with a man and a handmade telescope and 4 points of light. We have moved through 3.5 centuries of observation, through the Voyager flybys and the Galileo mission, and the Hubble auroral measurements and the Juno gravity data, and the Webb spectroscopy and the March 2026 thermal models. We have descended, in imagination, through 30 kilometres of ice, and into an ocean that has been warm for 3 billion years. That we have sat at a seafloor where the temperature is 120 degrees Celsius and the water is under enough pressure to stay liquid, and the chemistry has been reacting slowly and continuously for longer than the Cambrian explosion. We have asked the question. We have not answered it. Nobody has answered it yet. But the spacecraft is on its way, and while it travels, while the years between now and 2030 pass and the distance closes and the instruments prepare for their first measurements, the ocean keeps circulating. The seafloor keeps generating heat. The chemistry keeps reacting. Whatever is in that machine, microbes or complex organisms or nothing at all, keeps doing what it does in the dark, unobserved, unknown, patient in a way that only things that do not know they are being looked for can be patient. Although, where are you listening from tonight? If you are somewhere in the northern hemisphere and the sky is clear, step outside for a moment before you sleep. Jupiter is one of the brightest objects in the night sky for much of the year, a steady cream-coloured point of light, brighter than any star except the occasional Venus, unwavering where the stars twinkle. Find it. It will not take long, dimmed or. The light you see left Jupiter roughly 40 minutes ago, depending on where the planets are in their current orbits. 40 minutes ago, that light left a gas giant's cloud tops, crossed 400 million miles of empty space, passed through Earth's atmosphere, and arrived at your eye. In those 40 minutes, the orbital mechanics of the Laplace resonance continued their work. The tidal forces squeezed and released Io, Europa, and Ganymede, generating heat that has been flowing into 3 hidden oceans for billions of years. In those 40 minutes, whatever chemistry is happening at Europa's seafloor continued happening. In those 40 minutes, whatever is in that ocean continued being whatever it is. The light is old. The ocean is older. The question is older still, as old as the first time a human being looked up at a night sky and wondered whether anything else was out there. You're part of a very long chain of people who have looked up and wondered. Galileo looked through his telescope in January 1610 and saw 4 points of light that moved and wondered what they were. Voyager's navigation team saw a crescent cloud above Io and wondered if it was a moon they had missed. The Galileo spacecraft's magnetic field instruments detected a signal at Europa, and the seeing scientists in the room looked at each other and said the word that would not leave the literature for the next 30 years. Ocean. And now, 4.5 centuries after Galileo and 45 years after Voyager, we have a spacecraft the size of a tennis court crossing the outer solar system, carrying 9 instruments, heading for 49 passes over an ice shell that may be hiding the most significant thing we have ever found or failed to find. That is where we are. That is what is happening right now, while the world sleeps. This is a good moment to let go of the question. Not permanently, not forever, just for tonight. The question will be here in the morning. The ocean will be here in the morning. That the spacecraft will still be crossing the outer solar system, slightly closer than it was when you first started listening tonight, doing the quiet and extraordinary work of getting there. You do not need to hold all of this. You carried it far enough tonight. Let the ice hold it. Let the deep water hold it. Let the tidal forces of Jupiter squeezing and releasing these ancient moons, as they have for 3 billion years, keep doing what they do without requiring your attention. You've looked far enough tonight. The universe does not require you to solve it before you sleep. It only requires you to look and to wonder and to rest and to wake again tomorrow and carry the questions a little further. Rest now. The ocean is still there. The ice holds. And somewhere in the dark, and 30 kilometers beneath a frozen surface 400 million miles away, the water moves. It has always moved. It will move while you sleep. Sleep well.